Hello and welcome to this video in which we're actually going to output some text to the screen. So to recap what we wrote last time, we wrote a named block of code that is a function named main, which works as our entry point, and inside that named block of code, inside that main function, we wrote a return statement to indicate successful termination. So moving forward from this, to attain our goal of outputting text to the screen, we're actually going to need to use a piece of code written by somebody else, because it turns out outputting text to the screen is actually a more involved process than you might think. So to do this, at the start of our file, we're going to write #include. Now this is a command to a component of the compiler called the preprocessor, which acts before our source code is translated into machine code. In particular, #include means put some text in place of this line. So what text do we want to put here? Well, what we want to do is we want to open an angle bracket, type stdio.h, and then close an angle bracket. So the angle brackets instruct the preprocessor to look in a compiler-defined location for data with the name inside the angle brackets, which in this case is stdio.h. And here that is just a file name in some directory. But why do we just want to paste the text contents of some random file into the top of our C document? Why does that make any sense? Well, let's take a look at the version of the file I have on my machine. Now it turns out there's actually quite a lot of stuff in here, but the line we're looking for in particular is this one here. You might notice this actually looks a little bit like the syntax for a function which we've discussed previously, except from we have this weird Darwin alias thing and there aren't any curly brackets at the end here either. That's because this is actually what's called a forward declaration or a prototype of a function, which defines a function to exist without actually specifying the code relating to that function. In this case, this is because we're expecting the linker to hook up some code to this function name. As it turns out, most of the contents of this particular file, including the function fwrite, are actually part of the C standard library. So the functions in here are actually defined in the C standard. In C99, for example, fwrite is defined in section 7.19.8.2. And if we look at the standard in a little more detail, or just look at this definition here, we'll actually see that it takes 4 parameters. These are the location of the data to write, the number of things to write, the size of each thing, and the location to write to. So maybe we can call this function, invoke this named block of code, which hopefully the linker should hook up automatically because it's part of the C standard library, to output text to the screen. So let's try and call it and see what happens. In order to call a function in C, you first write the function's name, and then in brackets, you comma separate the parameters that function takes, the values that function takes to do its job, and then after that, we write a semicolon to tell the C compiler that we've finished with the function call. We've finished with this particular statement. So what parameters do we want to provide to fwrite? Well, first off, what do we want to write? Well, ideally we want to write some text to the screen. Now, a series of characters in C is called a string, and this can be denoted by double, note not single, quotes. So in this case, let's type the text hello world. Okay, so the next parameter, the number of things we want to write. Well, in this case, we want to write 13 characters to the screen because this string has 13 characters in it. And the parameter after this, well, each character in a string happens to be 1 byte in size, as we'll discuss later. Now, where do we want to write this data? Well, this is a little bit more difficult, but we actually want to write it to a place called standard out, written std out. This is something called a stream, a thing that makes data available over time, a lot like a conveyor belt. And this conveyor belt happens to lead to a place where programs typically write their output data. By default, this is usually the screen. So we can save this and we can compile. And we compile successfully, and if we run this, we'll see that actually, yay, we get hello world outputted to the screen. This is great. Now, of course, we can call the function numerous times if you want. This is part of the beauty of having these named blocks of code. You can just call them whenever you like, with different values if you wish. So maybe this time we just want to output the text hello. And that is 5 characters long, and each one is still 1, and we still want to write to standard out. So we can recompile, we can rerun, and great, that works too, but these have outputted on the same line, and actually this sort of part of my terminal prompt is outputted on the same line too. This is no good. We really want to separate these with a new line. Well, it turns out strings can also contain special characters such as new lines, and we can denote these using a backslash. So \n denotes a new line character, \t is a tab character, and if you're wondering, well, in which case how do I just write a backslash? I don't want it to be a special character, I just want to write a backslash, then you can write \\. But in this case, we just want \n, and then we should change our number of things to write to 14, because now we're writing 14 characters. So even though this string is textually 15 characters long, this \n is only 1 character, so we only want to write 14 characters to stand it out. And let's do the same with this one down here. We'll just add a \n, and we now want to write 6 characters. We can save, we can recompile, we can rerun, and great, it works. Now I should point out that just like everything else, strings just boil down to binary at the end of the day too. Strings in C typically use a standard called ASCII to link specific binary sequences to specific character values. So strings are then just sequences of these characters. These 1-byte ASCII values are just put next to each other to form textual strings. And we can actually prove I'm not lying here too, so don't worry too much about what I'm typing right now, because it's going to be some things that you don't quite understand yet, but try not to worry about it. But if I type the following, see actually what this means is it means, yeah, get the string hello world new line, and I want to return character 5 in that string. So character 5 is HELLO. So it's going to return O, and because the return type of our main function is int, that's going to get automatically converted to an integer value. So if we check the return value of our main function, we should hopefully see that it's the ASCII value relating to the character O, just to prove all of what I said about how strings are stored to be true. So let's save this, let's compile, let's run, and if we see the return value, we'll see, hey, it's actually 111, which is the exact ASCII character value for the lowercase letter O. Awesome. But again, try not to worry too much about that. That is literally just showing you how that works. I do not expect you to understand that by any means. Let's go back to where we were before. There we go. Now it turns out there's also a function in stdio.h, that's standard IO, standard input output.h, that's what that stands for, called printf. And printf is actually very similar to fwrite, but it writes to standard out by default, so we don't have to specify that. It also deals with counting the number of characters we want to output for us, so we don't have to specify that. And also it has some additional power which we're going to be using in future. So we can call that just like we call fwrite, but all we need to do is specify the string to output. So hello world, and that should work just as fwrite did, but it's a lot more convenient to use. So if we compile, we should see that that works just as we would expect. Great. So that's really all I have to say in this video. Tune in next time to hear about values that can change and getting input from the user and doing things with that input. See you next time.